Okay, so we're on question 2. The nuclei of some isotopes are radioactive. Which of the following statement could apply to the radioactive nucleus? Right, so again, we're going to use standard quality exam technique. It says 1. That means read all of them and eliminate the silly ones first. So, the nucleus will emit an atom. No, we're not going to emit an entire atom. The nucleus will emit light. I'm going to put a question mark next to that because gamma radiation moves at the speed of light. It is electromagnetic radiation, so they could mean gamma radiation. The nucleus will emit a neutron. Okay, so there is one example I know that where that does happen, and then the nucleus will emit sound. No, that's definitely not right. Okay, so we've got 2 to pick from. Okay, so the right answer here is actually the nucleus will emit a neutron, and that's the example you will learn if you're looking at, say, how a nuclear reactor works, and you see you have a large uranium-235 nucleus with obviously loads of protons and neutrons in it, and it splits into 2 smaller daughter nucleuses, and it spits out at the same time 3 fast-moving neutrons, which can then go off, strike a large uranium-235, and make that decay, which causes a chain reaction. So that's why this question is in here, I think. Potassium-40 is a radioactive isotope present in food, such as bananas. The following equation shows how potassium-40 will decay into calcium-40. Okay, give one similarity and one difference between the nuclei of potassium-40 and calcium-40. Okay, so if you have a look, numbers at the top have stayed the same. Numbers at the bottom have changed. So I'm going to say the similarity is it's still the same number of nucleons. Same number of nucleons, 40. And the difference is you must have had a neutron turning into a proton, so we have 1 extra proton. So that's 1 extra proton in calcium. Okay. The activity of a sample of potassium-40 is measured 3 times, and the measurements are given below. So you got 4906, 4956, 4889 Berquell. BQ stands for Berquell. Which of the following statements explains why the readings are different? Tick one box. Again, it's one box, so read them all. Radioactive decay is constant. Well, it's changing, so that means it's the exact opposite. Radioactive decay is hazardous. Again, this has nothing to do with it being dangerous or safe. It's talking about the fact they measured the decay rate 3 times and it was the slightly different numbers all 3 times. So it's got nothing to do with safety. Radioactive decay is random. Yes, that's what I would say as well. Radioactive decay is 100% random. You can never predict when a nucleus will decay. You can only predict the probability of its decay. Okay. Figure 3 shows how the activity of a sample of potassium changes over time. Looks like my bank balance at the start of the month towards the end of the month.
Stewie, hey.
Hey there. So, it's been 24 hours. Got my money?
Oh, you know what, just give me till next Friday, I'll have it for you.
Oh, that's funny. I could have sworn I said have it today.
Yeah, I don't have it, sorry.
Oh, well, all right then. That's good, OJ. Yeah, that hurt?
It's going down with time. Apart from I never keep my money for this long. Billions of years. So like I always say when you're reading a graph, eyes should go straight to the axis first, so mass of sample in milligrams and time in billions of years. Use figure 3. This is important, right? It says use figure 3 here. Right? Use. And that means put marks on figure 3. Okay? So if you're not marking the diagram, you could miss marks here. So use figure 3 to determine the half-life of potassium-40. Right, I've got to be really careful here then, because there's a couple of things going on. First, you've got to be able to read this graph properly. So between here and here is 200, because you go from 1000 to 1200. And there are 1, 2, 3, 4, 5 squares. So 200 divided by 5 is 40 per square. That's right, 200 divided by 5 is 40, right? So each of these little squares is worth 40. And where do I start at? I'm starting at a value of 1040, right? No, it's 2 squares, so 1080. Okay, so see how easy it is to make mistakes on these on reading graphs. So I've got to go from 1080 to half of 1080. So 1080 divided by 2 is 540. So I need to read down here to 540. Okay, so that would be 440, 480, 520. So 540 will be in between here and here. I'm actually going to get a ruler out. I've got a ruler in front of me, if you can see it. And I read across and down. Whoops. Right. Okay, and I'm getting, it took, so now I need to work out what the bottom squares are worth as well. So we go from 2 billion to 3 billion. From 2 billion to 3 billion in 5 squares. So that makes each little bit, right, it's 1 divided by 5, it's 0.2. Okay, each little bit is worth 0.2. So this is 1, 1.1, sorry, 1.2 and 1.4. So the answer is 1.4 million years. Okay, and the reason why you get 2 marks available is because they want to see this line and this line. And you can see there's a fair bit of thinking you have to do. You have to think about what these divisions are worth. These are worth 40 each, these are worth 0.2 each, so take your time and do it carefully and you should get all your marks. When food is eaten, some of the radiation the food emits is detectable outside the body.
Now what you see here is the radioactive dye we injected flowing through your husband's circulatory system.
But doctor, I haven't injected the dye yet.
Good Lord. Hi.
Which radiation would not be detectable outside of the body? Okay, so there are 3 types of radiation. You've got alpha, beta, and gamma. I always teach it as, think about... Okay, so this is a way I like to teach people a way of remembering all the different properties of 3 types of different radiations. So you can imagine that, what do they represent? Well, it's alpha, beta, gamma, alpha, beta, and gamma. Why have I chosen these to be this way around? Because in terms of which is the fastest moving, the tennis ball would be the slowest, then the beta particle, the air gun pellet, and then the gamma ray is the speed of light, just like a laser. So speed-wise, and it makes sense. It also makes sense in terms of which is makes it easy to remember which is the most ionizing. You go from the most ionizing to the least ionizing. So it's either you start at the most or the largest, and it goes to the smallest, or goes to the goes from the slowest to the fastest, or it goes from the most to the least. It's always in the same order. It's just you've got to know which side to start at. And I think the idea of a tennis ball and air gun pellet, etc., that helps to remember these things. So which is the most penetrating? Well, the gamma ray or the laser cannon from Star Wars would go through everything, and the alpha particle doesn't penetrate a piece of paper, or the tennis ball wouldn't penetrate a piece of paper. So I think that's pretty helpful.
How a tennis ball behaves, how an air gun pellet behaves, and how a laser from Star Wars behaves, so which is a laser ray, okay? So gamma rays can penetrate anything, beta particles are better at penetrating than alpha particles, but still not great. Maybe just make it
Aluminium. Alpha particle can't make it out of anything, so you could not detect the alpha particle outside of the body. Okay, I hope you found this useful. Thanks for watching. Please subscribe, like, share, and all that business if you found this useful.
Where's the money, man?